This is video 5.2 of the 8-week course in statistics, week 5, lecture estimation for single populations, video 2, estimating the population mean using the z-statistic. If a confidence level is given, for example, 95%, then we know the significance of tails. It is 1 minus the confidence level. After that, we can calculate the z-value, so that the area under the distribution between minus z-value and z-value is equal to the confidence level, in this example, 0.95. So, according to the central limit theorem, we are 95% sure that x bar minus mu over standard error is between minus z-value and z-value. It is equivalent to saying that with a probability of 95% the value of mu is inside the interval x bar plus minus margin of error, where the margin of error is the z-value multiplied by the standard error. Consider a random variable x. Take 100 samples of size n each. Calculate the average x bar for each sample. According to the central limit theorem, about 95 of the samples have the value of z between plus and minus 1.96. In other words, we are 95% sure that for any sample, the difference x bar minus mu over sigma over square root n is greater than minus 1.96 and less than 1.96. Let us solve a problem. A sample of size 44 yielded an x bar equal to 10.455. The population standard deviation is 7.7. Construct a 90% confidence interval. First, find the z-value. Alpha is 1 minus 0.9 or 0.1. So, the area to the left of the z-value is 0.05 plus 0.9 or 0.95. Z-value is the inverse of 0.95 or 1.645. Now use the formula for the confidential interval, where all values are known. The result is, we are 90% sure that mu is between 8.545 and 12.365. You could speed up the calculations by using the Excel formula for margin of error, confidence.norm from alpha, sigma, and n, or you could avoid the calculations using book 5, see the links in the description. The input is the confidence level in percent, sample size, mean, and standard deviation of the population. The output, standard error, z-value, margin of error, and the lower and upper limits of the confidence interval. Finally, you could solve this problem with the help of Colab 5, Cell 2, see the link in the description of the video. The input is shown to the left, the output to the right. We could solve the same problem for a higher confidence level, 95%, 98%, or even 99%. The higher the confidence level, the wider the confidence interval. We need to decide what we need more, confidence or the precision of the estimate. When we use samples of relatively large size, more than 5% of the population size, and we do the sampling without replacement, then it affects the standard error of the samples. The greater the sample, the closer it is to the population, so the standard error decreases. The formula for the correction factor is the square root of the difference between the size of the population and the size of a sample over the size of the population minus 1. Take it without the proof. The factor is always less than 1. When the size of the sample is equal to the size of the population, the factor is 0, and, according to the formula for the confidence interval, mu is strictly equal to the x bar, which is correct, because the sample in this case is the entire population. Let's solve the problem. A random sample of 50 out of 800 engineers of the company reveals that the average sample age is 34.30 years. Historically, sigma is 8. Construct a 98% confidence interval to estimate the average age of all the engineers in this company. The correction factor is the square root of 750 over 799, and, as a result, the confidence interval is slightly narrower than without correction. So far, we have been using samples with sizes over 30 because it was the requirement of the central limit theorem. However, if the original population has a normal distribution, then the distribution of its samples means is normal even for small sample sizes, and, hence, the formula for the confidence interval holds for small samples in this case. For that reason, solving problems with small n does not have any specifics, just make sure that the original population has a normal distribution. In conclusion to this video, let us resume the algorithm of how to estimate the mean of a single population when its standard deviation is known. First, check the conditions under which you can perform the estimation. The sample must be random, while the population distribution is not important. Sample size must be greater than or equal to 30, or the population's distribution must be normal. The sample's mean is known or can be calculated from the sample dataset. Significance alpha or the level of confidence is given. Second, calculate the margin of error as the product of z-value by standard error, or as the Excel formula for confidence.norm. Third, make the confidence interval as x bar plus minus the margin of error. Fourth, as an alternative to points 2 and 3, use Book 5 or Collab 5, Cell 2. Fifth, state I am 95, or other number, % sure that the mean of the population falls into the confidence interval of x bar plus minus margin of error.